Investigation of Power Consumption of Refrigeration Model and its Exploratory Data Analysis, EDA, by using Machine Learning, ML, Algorithm. Presented by Abbas Ahmed SN. Hussaini. Abstract. HVAC, heating, ventilation and air conditioning, play a vital role in various sectors, from residential and commercial to industrial applications. Understanding and optimizing the power consumption of these systems is crucial for energy efficiency and cost savings. This research aims to explore the power consumption of refrigeration systems during power on mode and perform exploratory data analysis, EDA, and machine learning, ML, algorithms to gain insights into factors influencing power consumption. The experimentation is conducted on refrigeration test rig and performance is calculated during power on mode by adding NPCM, nanophase change material, in evaporator section, and comparison is to be made without implementation of NPCM in evaporator section. By utilizing ML algorithms, it becomes possible to create predictive models that can assist in optimizing the power consumption of refrigeration systems, reducing energy costs, and minimizing environmental impact. The accuracy of model by linear regression is around 66% by implementation NPCM in refrigeration system, whereas 23% model accuracy is found without implementation of NPCM in refrigeration system. Also, it is observed that coefficient of performance of refrigeration system increase by around 15 to 18% as compared with without use of NPCM. Also, power consumption is reduces to 5 to 7% with implementation of nanophase change material in refrigeration system. 1. Introduction. HVAC systems are becoming more and more necessary for industrial facilities, residential complexes, and commercial buildings in India as its metropolitan areas grow. Perishable food product supply chains have grown in tandem with the majority of industrialized and developing countries' increased usage of refrigeration over the past few decades. These days, chilled or global supply chains for frozen food products, sometimes known as the cold chain, handle billions of tons of food. 1. Global food loss and waste occurs in 1/3 to half of post-harvest supply chains, with value chains pertaining to transportation, storage, and packaging suffering the most. 2 to 3. Globally, between 40% and 50% of fruits and vegetables are lost, with 54% of those losses happening during the production, handling, and storage phases after harvest. 4 to 5. Greater energy consumption brought on by urbanization necessitates the use of effective HVAC systems. Rising energy prices and environmental concerns in India are making energy-efficient HVAC systems more and more necessary. Therefore, in a world where resource depletion and global warming are at worrying levels, refrigerator energy efficiency has emerged as a critical component of the efficient management of electrical energy in the home. 7. HVAC systems that use less energy can save operational expenses and energy consumption by a large margin. It is possible to forecast when HVAC components, including fans and compressors, are likely to break down using machine learning algorithms. Uptime can be minimized and expensive emergency repairs can be avoided by scheduling maintenance proactively using real-time sensor data and historical data analysis. Demand response programs, in which HVAC systems are adjusted in response to grid demand, can benefit from machine learning. Systems can be temporarily changed to lower electricity usage during periods of high energy demand, which helps maintain grid stability. Machine learning, ML, is becoming increasingly essential in the heating, ventilation, and air conditioning industry due to its potential to enhance system efficiency, optimizes performance, and improves overall energy management. In order to manage energy demand and increase energy efficiency, thermal energy storage is utilized to store and release thermal energy. Only a few sectors, including building applications, cold chain, and refrigeration, and some industrial uses, are currently the focus of thermal energy storage and usage. But TES technology can be adopted for a wide range of applications as shown in Figure 1. As the most effective way to store food, refrigerators play a significant role in the home appliance market. To represent the linear relationship between predictor and response variables, a linear regression ML algorithm is employed. Python is used to implement this, with a Google Colab notebook serving as the front end. The normalized training dataset is utilized to train the linear regression model. Response variable optimal values are determined by adjusting different hyperparameters. 1.1 Important of thermal energy storage in HVAC system. TES systems enable the system to run during off-peak hours, when electricity is more affordable and easily accessible, thereby increasing the energy efficiency of refrigeration processes. In order to lower overall operating costs, the system can store excess cooling capacity when energy costs are low and discharge it when energy costs are high. Refrigeration systems' peak loads can be efficiently managed by TES systems. They lessen the need for additional chillers or compressors by storing excess cooling capacity during times of low demand and releasing it during times of peak demand. This helps prevent overloading the refrigeration equipment. Temperature control in refrigeration applications can be made more accurate and consistent with the use of TES systems. This is significant for a number of industries, including food storage, where the safety and quality of products depend on constant temperature maintenance. Fig. 1. Applications of thermal energy storage. 6. Maintaining ideal food storage temperatures is necessary for the transport systems that run these cold chain systems in order to guarantee maximum safety and premium shelf life. Because cooling systems are so good at keeping food, there is a growing consideration of their sustainability. It is necessary to approach the sustainability of a cold chain system from the perspective of overall cost. 7. PCMs are a class of latent thermoelectric materials that store energy by utilizing the solid-to-liquid phase transition. The large volume change makes the liquid/gas and solid/gas phase transitions less desirable from a technical standpoint. According to Sharma et al.'s Overview 8, the three main categories of PCMs are eutectic, inorganic, and organic materials. Latent heat storage has a larger volumetric thermal energy storage capacity than sensible heat storage. In many applications, it is observed that employing LHS is more attractive and competitive because less storage volume is required. 9. Thermal energy storage systems can be classified into several categories based on the method used to store and release thermal energy as shown in Figure 2. Latent heat storage requires a substance to undergo a phase change in order to store or release thermal energy. Phase change materials, or PCMs, are utilized to achieve latent heat storage. They can store and/or release significant quantities of energy during phase transitions due to their high heat of fusion. Thermochemical storage systems store and release thermal energy through chemical reactions. The heat that is absorbed or released as storage material transitions from a solid to a liquid, or from a liquid to a gas, or vice versa, is the foundation of a latent heat storage system. Its high storage energy density per unit mass in a quasi-static process makes it extremely appealing. 10. Figure 3 illustrates the vast majority of PCMs can melt and solidify at a variety of temperatures, which makes them appealing for a variety of applications. These PCMs are composed of hydrocarbon molecules, such as paraffin waxes. They are frequently utilized in many different applications due to their reasonably low cost and moderate heat storage capacity. Inorganic PCMs are composed of salt crystals that have absorbed water molecules, such as calcium chloride hexahydrate and sodium sulfate dihydrate. The hydrate crystals disintegrate into a lower hydrate and water or into anhydrous salt and water at the melting point. Sharp melting and solidification points are made possible by the eutectic composition of the various salts or other compounds that are combined in these mixtures. Since eutectic crystals freeze into a close-knit mixture of crystals, they almost always melt and freeze without segregating, leaving little leaven. Refrigeration is essential because it increases the shelf life of perishable foods and gives consumers access to safe, high-quality organoleptic food. In fact, perishable food changes like microorganism growth, ripening rates, browning reactions, or water loss occur less quickly at low temperatures. Perishable food product supply chains have grown to keep up with the expansion of refrigeration use over the past few decades in the majority of developed and developing nations. In order to guarantee product quality for consumers and to lower food waste and health hazards, temperature control in the cold chain is crucial. 12. It is anticipated that cold chains will make extensive use of wireless temperature sensors and data transmission, which will yield a lot of data. This enables the compressed sensing method to assist in the real-time temperature analysis. This enables autonomous warning systems to take equipment temperature variability into account in addition to time temperature thresholds for alarms. Our understanding of cold chain failures, including their occurrence, severity, and length, will increase with long-term data analysis using a machine learning methodology. Machine learning models may be trained using the experimental and numerical data obtained from cold chain studies. 13. 1.2 Machine learning scope for HVAC industry. Using machine learning, food process optimization procedures can be facilitated by building a model that predicts the optimal result based on the input data. Machine learning includes supervised and unsupervised learning, feature engineering, data pre-processing, model selection, evaluation, and optimization approaches. Numerous problems involving the optimization of food processing could be resolved with these techniques. Machine learning is being used by the food sector more and more to improve consumer experiences, reduce waste, and boost production efficiency. In addition to automating tasks like labeling and packaging, machine learning can be used to predict customer preferences and create individualized products as shown in Fig. 4. It can also be used to maximize ingredient utilization and reduce costs. 15. Using a sensor-based system, ECTA Sunwani ETAL16 present a novel method for monitoring and analyzing food spoilage. Food can be preserved with the gadget this study suggests for a longer period of time. Furthermore, food items can be kept fresher for longer by extending their shelf life. It keeps an eye on the quality of the food items and keeps alerting the user via voice-activated commands or a display. It also generates alerts that indicate how long the food is expected to spoil. The suggested gadget has a 95% accuracy rate. The suggested smart device can be made better by using machine learning and image processing algorithms to identify early spoilage. Machine learning was proposed by NV Ganapathy Rayu ETAL17 to predict the fridge door status, open or close. The target variable is the fridge door status, 1 or 0, and the features that are used to train the model are tray temperature, fridge cabinet temperature, and energy consumption. The suggested works goal is to use machine learning algorithms to determine the fridge door's current status. Zara Saltani et al. 18 in order to diagnose 20 distinct sorts of defects at once as well as non-faulty conditions in the industrial Rs, various classifiers are compared. The training set comes from a simulation model that was employed in the BITZER system control development process. The findings show that how well the training data reflects the operation regime has a significant impact on the algorithm's problem detection reliability. It is also shown that when the verification data is obtained from various system configurations, a well-trained support vector machine, SVM, can accurately categorize 20 different sorts of faults at once with 95% accuracy. The involvement of machine learning in healthcare applications in the current context will be covered throughout this paper by Sane Rath Mutilaj Don Alexis Chinthekajadalake et al. 19 together with an explanation of the main machine learning techniques and algorithms being applied to healthcare decision-making. It was evident from the data gathered, which was made possible by the high processing power of modern, sophisticated computers, that neural network-based deep learning techniques had performed exceptionally well in the field of computational biology and were widely employed because of their high reliability and prediction accuracy. Machine learning is used in the diagnosis of illnesses and biomedical event extraction, medication repurposing, medical imaging, prediction, and much more in the healthcare industry. While described the use of ML in cancer prediction and prognosis, Konstantina Kuru et al. 20 talked about its concepts. In an attempt to accurately foresee disease outcomes, Most of the studies that have been presented in recent years focus on developing predictive models using supervised machine learning techniques and classification algorithms. Their data analysis demonstrates that diverse feature selection and classification techniques combined with the integration of multidimensional heterogeneous data might produce valuable tools for inference in the field of cancer research. 2. Proposed experimental methodology and machine learning implementation. 1. Experimental setup consists of refrigeration test rig along with vapor compression refrigeration components like compressor, condenser, expansion device and evaporator. Locate temperature sensors, thermocouples, at crucial points, storage unit, evaporator, and condenser, etc., and pressure gauges are used to record pressure of condenser and evaporator side. 2. Nanophase change material, eutectic mixture, for lower temperature applications based on their phase change temperature, latent heat, thermal conductivity, and stability is selected for experimentation. 3. Preparation of nano-PCM is done by using ultrasonic agitator and magnetic stirrer by holding mixture for 30 minutes till nanoparticles get mixed with PCM mixture. 4. Start the system and initiate the refrigeration cycle. Conduct the experiment during power on situation without consideration thermal energy storage in evaporator section. Record the readings like condenser and evaporator pressure and temperature at certain interval of time. 5. Data is collected till cabinet temperature reaches at 00 C and achieve constant cabinet temperature as per system design capacity and calculate coefficient of performance, energy consumption, etc. 6. Same process is repeated by adding NPCM in evaporator or section as thermal energy storage and performance parameters are calculated and compared. 7. Exploratory data analysis is done by consideration of different measured performance parameters. 8. Implementation of machine learning algorithm, linear regression, for power consumption data and accuracy of model is calculated and compared. Also prediction study is done to know the power consumption at particular time interval. In order to train models for prediction and decision making, supervised learning techniques such as regression and classification use labeled training data sets. The primary distinction resides in the fact that the classification algorithm classifies the data for the ease of making decisions later, whilst the regression technique is primarily employed for fitting, bringing the fitting line as close to all data points as feasible. The regression algorithm is mostly used for prediction. 22. Implementing a linear regression algorithm involves several steps as shown in Fig. 7. 3. Experimentation and results. The refrigerant passes through copper tubes in the evaporator section between the stainless steel inner and outer sections of the cooling chamber. The NPCM, eutectic mixture of 15% CaCl2 plus 15% KCl with water as base fluid as PCM and 1% graphene act as nanoparticle, is kept between annular space of evaporator and insulated cabinet. Experiment is conducted during power on mode by implementation of NPCM and its comparison is done by without implementation of NPCM. The temperature and pressure data is collected from data logger and it is saved in CSV format. The evaporator call absorb the heat from NPCM mixture during power on mode and NPCM start changing phase from liquid to solid till evaporator reach at 0 to -50 C. During charging process of NPCM it store latent heat and dissipate that heat during power off or temperature fluctuation exists and change its phase from solid to liquid. The data sheet consists of different total 14 columns, float and integer format, which includes different temperatures, time, pressures, performance parameters like power consumption, COP, voltage, and current, etc. for both datasets like with and without NPCM. The data is available in CSV format. The chosen datasets is useful for exploratory data analysis. EDA helps in identifying outliers, missing values, or anomalies within the dataset. These anomalies can significantly impact the results of statistical analysis if not handled properly. The experiment is conducted during power on mode with and without adding nano-PCM in evaporator section and different parameters like power consumption and COP. Coefficient of performance is calculated by recording different temperatures of test setup as shown in Figure 9 and Figure 10. For experimentation, eutectic mixture of phase change material, CaCl2 plus KCl, along with graphene nanoparticle with water as a base fluid. It is observed that coefficient of performance of refrigeration system increase by around 15 to 18% as compared with without use of NPCM. Also, power consumption also reduces to 5 to 7% with implementation of nanophase change material. After conducting the experiment, it is observed that, implementation of NPCM in evaporator section, it is possible to attain constant temperature for longer duration of time even though temperature fluctuations occurs due to frequently opening and close the door of cooling cabinet. The purpose of using nanoparticles with phase change material is poor conductivity and relevant thermal properties of PCM. By addition of nanoparticles, heat transfer and thermal conductivity of PCM is improved. The selection and percentage of PCM and nanoparticles is decided on the basis of previous research. 23. It is decided to do exploratory data analysis of experimental result. Displot is used to create distribution plots to visualize the distribution of a single variable like temperature as shown in figure 11. It is observed that condenser inlet and outlet temperature is lie from 45 to 60 degrees Celsius and 25 to 38 degrees Celsius respectively. Evaporator inlet and outlet temperature is lie between 0 to 25 degrees Celsius and 0 to 15 degrees Celsius respectively. Also, cabinet, cooling box, temperature will maintain from 0 to 5 degrees Celsius. Fig. 11 Displot of temperature distribution by use and without use of NPCM during power on. Also, kernel density estimation, KDE, plots, which are used to estimate the density function of a continuous random variable of temperatures during power on mode as shown in figure 12. Fig. 12 Difference of temperatures distribution by use and without use of NPCM during power on mode by using KDE plot. When working with multivariate data, pair plots helpful since it makes it easy to see the relationships between many variables like temperatures, coefficient of performance and power consumptions, etc. as shown in figure 13 and 14. A data visualization method called a strip plot is used to show individual data points on one axis, usually in opposition to a categorical variable on the other axis. In figure 15, results of COP, power consumption, and cabinet temperature is scattered along with time. Subplot is a function used in many plotting libraries, like Matplotlib and Seaborn in Python, to create multiple plots within a single figure. This allows you to visualize multiple sets of data or related plots in the same graphical space. In figure 16, subplot of power consumption is drawn. It is observed that power consumption during power on mode by implementation of NPCM is less as compared to without NPCM. Linear regression mostly used for finding out the relationship between variable and forecasting. Linear regression performs the task to predict a dependent variable values, y, based on a given independent variable, x. In this experimental research, only one feature is considered, so linear Angrosian model is used. This hyperparameter is not typically associated with standard linear regression. Instead, learning rates are essential in optimization algorithms like gradient descent used in iterative methods such as stochastic gradient descent, SGD, for solving ridge regression or lasso regression problems. For standard linear regression, without regularization, the key aspects are often more related to the data pre-processing, such as handling missing values, feature scaling, and feature selection. In the context of regularized linear regression, ridge or lasso, alpha is a critical hyperparameter that controls the strength of regularization. A higher alpha value corresponds to stronger regularization, which penalizes the model for large coefficients to prevent overfitting. However, when regularization techniques like ridge regression, L2, or lasso regression, L1, are used, the hyperparameter tuning process becomes more relevant, focusing on selecting an appropriate alpha value to balance between bias and variance in the model. After experimentation, linear regression algorithm is preferred to predict the power consumption during various time spans, and after implementation it gives 65% model accuracy. Linear regression is imported from sklearn.linear_model library. Also available data is given to training and testing purpose. Also slope, intercept, predicted value, and error are calculated for generating model accuracy. In Figure 18 and 20 different inputs are provided to algorithm to find out the actual and predicted values of power consumption with error values. An effective and popular technique for simulating relationships between variables is linear regression. It offers a simple method for forecasting and interpreting how predictors affect the result. In the fields of statistics and machine learning, linear regression is a basic and often used procedure. It is usually used to represent the relationship between a dependent variable and one or more independent variables by fitting a linear equation to the observed data. Conclusion. The purpose of nano-PCMS is to optimize the thermal energy storage capacity by utilizing the distinct characteristics of nanomaterials. Through enhanced thermal energy storage and heat transfer efficiency, nano-PCMS can help reduce energy consumption and operational costs across a range of industries. Investigating how much power refrigeration systems use and combining machine learning, ML, methods with exploratory data analysis, EDA, have produced insightful findings with real-world applications. Correlations and patterns found by EDA help us comprehend how different elements, such usage patterns and temperature settings, interact to affect power consumption. The findings of this study have a direct impact on the marketing of energy-efficient refrigeration systems. Once nanophase change material is used in refrigeration model as thermal energy storage, this study's ideas and models can lead to significant energy and cost savings, making it a crucial contribution to sustainability programs. In conclusion, the application of machine learning technology has a lot to offer the refrigeration sector. Machine learning lowers costs, lessens environmental impact, and improves product quality and safety by maximizing energy efficiency, enabling predictive maintenance, and improving overall system performance.